Welcome everyone to the fourth Direct Right Lithography workshop and its RIEH webinar series. Before we start, I'd like to acknowledge the traditional owners of the land we're gathered here today, which are in my case the people of the Kulin Nations, and I'd like to pay my respects to their elders, past, present, and emerging. Furthermore, I'd like to acknowledge the Australian National Fabrication Facility and its CEO, Jane Fitzpatrick, for their ongoing support of our workshop. And of course, our panelists who helped to facilitate the RIEH webinar series, and for today's webinar, especially Jörg Hübner and Henry from the DTU, who introduced us to Rod, who will shortly introduce Christina. And of course, our sister conferences and workshops, such as the Zurich Nanofabrication Days, the 3Beams meeting, NanoFab UK, and the Mabel meeting. And of course, all of the team members of the Direct Right Lithography Workshop Organizing Committee for their hard work to putting this together. And with this, I'll hand over to Rod, who will introduce Christina for today's webinar, Helicon double layer thrusters, a radio frequency plasma source with many applications. I have one more slide, because I actually looked up what Wombat actually is. So Christina or Rod, if you want to say a few words around this, please feel free to do so. Okay, Rod, the stage is yours.
Thank you very much. It's a pleasure to introduce Christine Charles. Christine was born in Finistère in Brittany, which is the end of the world, which we nearly approached at 10 o'clock today, and gained a degree in engineering from the University of Rennes and a PhD in plasma physics from the University of Orléans. For the past 3 decades, she has worked at the Space Plasma Power and Propulsion Group that she now leads at the Australian National University, and she has achieved a very high level of professor. Her scientific excellence has been recognised in a variety of manners, but perhaps I should mention her fellowship of the American Physical Society and her fellowship of the Australian Academy of Sciences, both fellowships not easily given. She also has a degree, which is nice, in jazz composition and has written a suite for 4-stringed instruments in the Ghibli style. So there you go, a true Renaissance woman comes to us from Brittany. So I'll hand over to Christine now.
Okay, thank you very much. I'm now going to share my screen and start the presentation. Thank you very much for the introduction and for the invitation to give this talk, which should now be coming up. If I just do a full screen, and hopefully everyone will be, and now.
Looks good.
Yeah, but I can't move does it look okay?
Perfect.
Perfect. So please feel free to interrupt. It doesn't really matter. This is really relaxing event. So today I would like to present slides on the Helicon double layer thruster for space use. So this is a radio frequency plasma source with many applications. So this is, of course, on behalf of the Space Plasma Power and Propulsion Group at the Australian National University, and on behalf of many of our collaborators worldwide. So thanks again for the invitation. So here you have a series of photos and pictures, our beautiful sun, a satellite orbiting around the Earth, a computer, a wafer, silicon wafer, some deep trench, a same photograph, and a fluorescent tube. So what is a common link between these? That's always what I ask the students. And the common link is the 4th state of matter, which is the plasma state. So plasma is very interesting. It's a hot ionized gas containing electrons, ions, neutral particles, and photons. So all stars and the interplanetary material is plasma. So 99% of the visible matter in the universe is in the plasma state. So I'm not talking about dark matter here. So because it contains charged particles, the basic macroscopic description will require to use at least 2 fluid components, that of the ions and that of the electrons. And these charged particles have very different masses. And they respond to electric and magnetic fields via the Lorentz force, F equal QE plus V cross B. Additionally, collision processes between particles and the physical chemistry within the plasma, and also at its boundaries or sheaths, that's very complex. So what is complex usually means that there is also a way of finding or developing applications which makes this field really interesting. So today I will be talking a little bit about these applications. But I just wanted to use the first example of water, which is simple enough, right? H2O. So to go from water vapor to a water plasma, what do we need to do? Well, we need to heat up the system and start breaking the H2O molecules, breaking the OH covalent bonds and taking electrons off so that we'd end up with positively charged ions. And in the process, you will have also emission of light. So you can see here a photo of a typical water plasma. And when you do that and you think a little bit more, you can see that a water plasma is already really complex because you can have a variety of components. You have the molecular components, hydrogen, oxygen, water molecules. You have the atoms, hydrogen, oxygen, the radicals, OH, and you have positive ions, negative ions, electrons, photons. So it's already a big soup. And each of the species will have its own temperature, often defined by a Maxwellian distribution. In addition to that, there will be many excitation states and vibrational states, especially since you have molecules in the system. But let's assume that we keep going, put more energy into this system, and what we'll have is we'll be able to remove all the electrons. The ions will go fast enough to overcome the Coulomb repulsion, and we will end up with reactions between the nuclei. So this is actually what happens in the sun. So the sun is the hottest plasma in our solar system. It runs on hydrogen. So at its center, the temperature is about 15 million degrees, so really hot indeed. And at the surface, it's about 6,000 degrees. So the main reaction is the fusion of the hydrogen atoms forming helium nuclei, and with the release of a lot of energy in the form of radiation and solar wind. So we don't really need to worry too much about the supply now. It's about half into its age. So we still have 4.5 billion years of light and heat supply. But this is the best example of a plasma in our solar system. Now, what happens with the sun is that it also creates the solar wind, which is now an expanding plasma, which expands from the surface of the sun into the universe and impacts onto the upper layer of the Earth's magnetosphere. So this is what creates the aurora. So on the left here, you see the visible corona, which is what you would see during a total solar eclipse. So this is actually a nice photo of the solar wind. So that solar wind then generates the aurora at the north and south poles of the Earth. And so that's the best example of a plasma near us. So the other example is that the layers of atmosphere close to ground are neutral. But if you go high enough, you have the ionosphere and magnetosphere layers in the Earth's atmosphere, and these are plasma layers. So these are naturally occurring plasmas. Another example of naturally occurring plasma around the Earth is a lightning strike, which you can see here on the right-hand side. So in summary, the solar corona is a low pressure, high density, expanding plasma and expanding in a diverging magnetic field. We'll talk about the coronal funnels later on. What's important here is that solar wind and coronal mass ejections determine space weather. So our Earth grid is subject to space weather events, and also all the satellites orbiting around the Earth are subject to the health or to the activity of the sun. So we can't ignore this. Fortunately for us, except for scaling, the parameter ranges of both the coronal plasma and plasma arc jets, such as in this lightning strike, these parameters can be achieved in the laboratory and tailored to suit many applications. So other than the aurora, the ionosphere, the magnetosphere, and the lightning strikes, we don't really have the plasma state occurring naturally here in our everyday life. So we need to work on this. So today I'm going to focus on plasma thrusters for space use. But we have to acknowledge that most technologies developed for space contribute to technologies used on Earth and vice versa. So it's the same physics at the end of the day, and it generates a lot of development in the engineering world. So let's have a look at a plasma. So on the top left-hand side here, if you generate a plasma at atmospheric pressure, usually it will look like a corona discharge or a lightning strike. So here we have a Tesla coil, which is brought close to a grounded metallic surface. If you want to generate a glow discharge or a larger volume of plasma, you are going to have to decrease the operating pressure. So when you decrease the pressure, you go down this arrow here. And here you have examples of glow discharges or plasmas that we use to develop plasma thrusters. So here, the pocket rocket is about a few millimeters in size, typically a cylindrical discharge and a few torr of operating pressure. Then we have a dual stage 4-grid thruster, a bit more lower pressure. And then we have the Helicon double air thruster on the bottom right here. So when you want to go from atmospheric streamers to glow, you decrease the pressure and you also work with the size because it's related to the PD parameter. And then you need to bring your electrical power into the system to ionize the gas and produce a plasma state. So you can use DC, radiofrequency, or microwave. And you can have internal or external electrodes, also called antennas, to do this. And if you work with charged particle extractions and acceleration, you need to worry about neutralization, and I will talk about that as well. So let's have a quick words about electric propulsion in space. So of course, to get off the Earth, you need to use chemical rockets, which provide a lot of thrust for a short time and burn a lot of propellant. But once you are in orbit or in space, you can you can deploy electric thrusters. And then the plasma states becomes useful because the propellant is heated and ionized, and you can use electric and magnetic fields to accelerate this propellant mass and create thrust. So usually the thrust will be much lower in magnitude compared to chemical thrusters, but the main advantage is that it has a very good fuel efficiency, and this is normally defined as what's called the specific impulse. So mature technologies can be seen here at the bottom, and they usually use a xenon, krypton, or argon as a propellant. They are not easily scaled up or down, and they may have erosion issues. So on the bottom left here, you have an ion graded thruster. So you can see the plasma and the light coming out through a grid there. So in fact, what you have is at the back, you have a plasma cavity, and you have a system of grids to extract and accelerate the ions. So you can see this little red circle here. This is usually a hollow cathode or electron neutralizer. To be able to have the release of these accelerated ions into space, you need to neutralize them by injecting electrons so that it's a neutral system that leaves the thruster and generates thrust. On the right-hand side here, you have an example of the Hall thruster or Hall effect thruster. This is a very interesting thruster. It actually has a system of coils to generate a transverse magnetic field. So the physics is a little bit more complicated, as we've seen with the Lorentz force. And this particular thruster was part of the SMART 1 mission that was a European Space Agency mission. So it went to the moon in 13 months, which is a long time, but with only 53 kilograms of xenon. So that's typically what I mean by higher specific impulse. It can go a long way with very low amount of propellant. But we work a lot with radiofrequency plasmas, and that's also used a lot in the microelectronics industry and for etching, deposition, etc. So let's have a look at how we can create the plasma. So I said before, it can be DC, RF, or microwave. I'm going to focus about radiofrequency. The left-hand side schematic here is a typical capacitively coupled radiofrequency system, which would have a powered electrode and a ground electrode, and you have an oscillating radiofrequency voltage applied to the electrode, and you would put your sample on either of these two electrodes, depending on your process. But we like to work with radiofrequency plasma sources which have an external electrode. So usually you have a cylinder and a loop antenna wrapped around this glass or ceramic tube. And now we actually work with an oscillating antenna current here. And consequently, you also have a dB/dt as a main parameter. We need to say that there will always be an impedance matching system with a resonant circuit. So there will be also a high voltage on this antenna. So we will have usually a mix of some capacitive coupling with inductive coupling in terms of coupling of the electrical power to the gas to ionize it and make it a plasma. So in thrusters, usually you have a plasma system and one end of this plasma cavity will be open to space and may have a system of grids to generate thrust. We can make these RF thrusters or sources a little bit more complicated in terms of physics, but a little bit more efficient by adding an axial or two axial solenoids and generating a BZ component. That's a DC field superposed with a dB/dt. And what happens here is very interesting. So on this graph on the right, we have plotted the measured density as a function of a radiofrequency power injected in a cylindrical plasma system. And you can see that you go through three different modes. The first mode is what we call the capacitive or E mode. And the density, plasma density, is a function of the square root of the radiofrequency power. And then we move to the inductive mode, where the density is now linear with the power. And then you can access wave modes, and the density becomes an exponential function of the power. So that means you get really high plasma densities, which are really important for plasma processing and also for generating more thrust. So in the thrusters I will talk about today, the pocket rocket is typically in these first two modes, and the Helicon double layer thrusters may be in the second two modes, H or W. So Helicon waves can propagate in the W mode and deposit power in regions which are inaccessible to capacitive or inductive modes. So they have been studied for decades, and they are still studied a lot all over the world. So with a magnetic field, you can actually just have a simple, very uniform axial field, or you can play with converging, diverging nozzles, or with just diverging nozzles. So we have the HDLT, we have the Helicon thruster, and we have also the Vasmir American rocket. So you can check these out if you want. So now I'm going to talk a little bit more about the Helicon radiofrequency device, which was at the heart of the Helicon double layer discovery. As I said before, you can have just a cylinder in which you're going to create your plasma. You have your radiofrequency antenna wrapped around it. There are different types of antennas. You can just have loop antennas, double saddle field antennas, or called Nagoya type antennas, Helicon antennas, and they can generate different wave modes. So in this double layer experiment, we just generate a plasma. We have two solenoids which generate an expanding magnetic field from this plasma, which diffuses into a larger contiguous vacuum chamber, which is pumped down. So this chamber can be equipped with a system of probes, and an important probe is what's called an energy analyzer. Under certain conditions, corresponding to a diverging field and a rather low gas pressure, less than a few millitorr, what happens is the plasma exhibits a high plasma potential in the plasma cavity, and there are issues with wall charging of this insulating cavity, and the plasma decides to create its own plasma potential drop here near the exit of the plasma source. What does that mean? That means that all the ions created in this plasma cavity will see this sharp drop in potential and this electric field and will be accelerated and reach high velocities. What's also interesting is you have electrons which will be able to overcome that potential barrier and it will neutralize the ions. So this is essentially the basic physics behind this abrupt potential drop. And such a potential drop is similar to a double sheath within a plasma. And it's called a double layer. So how did we demonstrate this? Well, we had an ion probe, which was in the path of the beam. And you can see here on the right picture. And so at the bottom here, you have the ion energy, and then you have the radius. And we saw that in the projection of the plasma source, we measured a 50 eV ion beam, which corresponds to an ion velocity of 10 kilometers per second in argon. And it had quite a large surface area. And so if you now rotate the ion energy analyzer, this beam stops appearing or being measured. So that's a demonstration that it's really generated by the double layer, confirming the essence of the double layer. So that's what the experiment actually looks like, just straightforward. We have inductive/Helicon RF source on the left, a diffusion chamber, a system with pumps, and here at the bottom you can see the plasma which is diffusing from the source to the bigger diffusion chamber. So I'm going to talk a little bit about the physics of this double layer. So a double layer corresponds to a sharp drop in plasma potential, which is this phi potential, the black line here. So when you do the first derivative of this line, you obtain the axial electric field. This is the electric field that will accelerate your ions out of the plasma source. And if you do the double derivative, you can get the charged particle profile, and you can see that you have a layer of positive charges against a layer of negative charges. So this is what a double layer is two layers of opposite charge next to each other, sustaining a self-consistent electric field within a plasma. And there is no internal electrode. It's important to understand this. So we have created an acceleration mechanism by being able to generate this double layer without using grids or internal electrodes. This is really important. So usually this potential drop has to be much larger than the electron temperature and has to be over a narrow distance for the definition of a double layer. So double layers have been measured in the aurora for a long time, but in the aurora, people say that these are current-driven double layers. So in the aurora, there would be an actual net current through this system. However, with the Helicon double layer system, there is no net current through this. So it's called a current-free double layer. So it generates particle acceleration and beam formations without using electrodes, and there's no net current going through it. That's the major physics behind this system. So how do we make a Helicon double layer thruster out of this? So you have a photo on the right-hand side here. Well, you need to do a bit more experimental physics before that. On the left here, we have measurements of the plasma density from the plasma source to the diffusion chamber, and you can see the magnetic field lines. On the right-hand side, we actually have measurements of the shape of the double layer, which is this blue, purple kind of cone here. And we have measured accelerated ion beam in terms of this yellow to red flame. So we have demonstrated that this current-free double layer can be generated by the plasma itself in a multitude of plasmas, argon, xenon, oxygen, hydrogen, methane, etc. It's a spontaneous system, and I will now briefly go through point 1, 2, 3, show how it's important for understanding the Earth's aurora, how it may be related to the solar wind acceleration, and how it can be effectively used to generate an electronless space engine. So just one slide on the black auroral arc. So I guess everyone's aware of these beautiful auroral patterns here. But people have postulated that it's actually an ensemble of electric field formations which can have either inwards pointing electric fields or outwards pointing electric fields. So the inwards pointing electric field systems corresponds to electrons being accelerated towards the Earth and ionizing the nitrogen and oxygen, producing these green lights. But in the middle, you can have what's called auroral or black auroral arcs, and these correspond to outwards looking electric field. And this is exactly what we have measured in this double layer RF system. You can see this potential structure. So we propose that this could be a spontaneous phenomenon in terms of a current-free double layer existing in the Earth's aurora. Another application is the coronal funnels. So the solar wind is really interesting, and there is unexplained acceleration of the solar wind from the distance of 5 mm here to 20, from 0 kilometers per second to 10 kilometers per second. What's really interesting is in the laboratory, we measured about acceleration of about 10 kilometers per second. And if we look at the structure of the magnetic field at the surface of the sun, it's very similar to a diverging magnetic funnel. And on top of it, the value is also very similar because at the surface of the sun, you have different types of magnetic field lines. You've got the ones that fall back on the surface of the sun, and you have a system of coronal funnels, and the magnetic field at the bottom of the funnel is about 120 Gauss, so very similar to our system. So we have proposed, since we know that the double layer works in hydrogen plasmas, we have proposed that there could be current-free electric double layers spontaneously being formed in the solar wind and generating acceleration of ions to the values of about 10 kilometers per second. And you may have heard that there is currently the NASA's Parker Solar Probe mission happening, with which will crash onto the sun and go through the solar corona and will try and get some insights into the solar wind acceleration physics. So all this is a very active field of research. Now, so we've talked a little bit about ion acceleration with this double layer system, but let's have a look at electron transports. If you do plasma processing of wafers, you know that you have to think about ions, you have to think about active radicals, and you have to think about what the electrons are doing, because the electrical power is given or transferred to the electrons, and then the work is done by the electrons to generate the ions and modify the distribution functions. So top right here, you have a typical double layer system where you have your potential drop. And of course, if there's a potential drop, there is an electric field which will accelerate the ions, but it will actually trap most of the low energy electrons on the left-hand side here. So the plasma retains these electrons to keep ionizing the gas. The electrons are accelerated towards the right. The ions are accelerated to the right. But what's really interesting is the tail of the distribution. The fast electrons will be able to go with the accelerated ions and neutralize these ions. So on the bottom left here, you have a typical electron energy probability function curve, which is measured in the laboratory. And as you can see, it has a depleted tail. So the electrons, which are trapped in the helicon source, have a temperature which is higher than the tail, because the tail is actually the part that can overcome the potential barrier of the double layer. So if you go downstream of the double layer, you just measure this tail. So this again is a confirmation of the physics of the double layer. And you can push this further. You can work on electron and absolute energy states. And you can do a little bit more analysis of what happens with an expanding plasma, such as the solar wind. And usually when you do this, you do what's called a polytropic analysis, where you plot the effective or average electron density as a function of the effective electron temperature. And you get a profile. So when the plasma expands, it's really an adiabatic process. There's no heat absorption with the surroundings. So in theory, it should give us what's called a polytropic index of 5/3. However, with our experiments, we measure a value which is lower. And these values have been measured by spectroscopy of the surface of the sun using the Hinode satellite, which was a Japanese satellite. So I won't go any more into these details, but I just want to say that this physics is very important. It can be related to a lot of space physics. And now I'm going to see how we can get the essential physics and apply it to engineering. So let's move to the Helicon double layer thruster. So we have a plasma source, inductively coupled. There may be a wave, it doesn't really matter. It's an inductive radio frequency plasma source, which can generate a supersonic ion beam, which will be neutralized by electrons. So the double layer does all of this. You don't need to worry. We don't have electrodes within the plasma, so there's no erosion issue. As long as you have propellant and power, you can have an extended lifetime for your thruster. And there is no moving parts, so nothing can break, really. Helicon sources are scalable in power and size. We can make them small, big, put a lot or not a lot of power. So we have been collaborating for decades with NASA, ESA, Airbus, Lockheed to develop this Helicon thruster. So the idea is that the thrust is dmVdt. And since we're working with accelerated ions, the dmdt is the flow rate, and we are trying to increase the ion exhaust velocity. So then that gives you the value for the specific impulse here. And we have the efficiency of a thruster, which is how much thrust you get per radio frequency power that you put in. And usually for any space mission, you have what's called the delta V of the mission, which will be related to the specific impulse and to the dry mass of the satellite and the mass of your propellant. So to develop a thruster, you need to be able to measure the thrust. And the thrust is like a complementary diagnostic to plasma probes, such as energy analyzers and Langmuir probe, etc. So here on the left, we have our inductive source, and we have an open end of this source. So what are the components generating thrust? So we have demonstrated that if you suspend this, I'm going to call this source a thruster, a plasma thruster. If you attach it to a pendulum or thrust balance, and you do a variety of measurements, you can find out that there are three main components to generating this thrust. The first one is this in green here. It's called the sheath thrust term. It corresponds to a push on the back of the back end of the cavity. The second one is what's called the magnetic field components. So this is a little bit more complicated. So when you have a magnetic field in a plasma, you will see that you have two types of drift that can occur. You have the E-cross-based drift and you have the diamagnetic drift. So in the Helicon thruster, we are actually dealing with what's called an electron diamagnetic drift current, which forms here near the exit of the thruster, and that creates, via the Lorentz force, creates a push on the magnetic field lines. So this is this blue component. And we have also shown that we have a friction term which decreases your thrust which is in bottom term here. So our collaborator in Japan is really focusing on the high power thruster up to kilowatts, and we are focusing on more a few hundred watts or even a few tens of watts. But the ISP can be quite high, of the order of 3,000 seconds per argon. The thrust is not huge, but it's decent, and the radio frequency efficiency, the power efficiency, is a little bit low, so that's what we are working on at the moment. And how did we measure these components? Well, we did something which was really very interesting for us. We had a system where we only attached the solenoid structure to the thrust balance, and we measured this term TB, and we had another system where we only attached the plasma cavity to the thrust balance, and that's the way we separated these components. And then we measured the plasma characteristics and correlated these components. So in the Helicon double layer thruster, or I'm just going to talk about the Helicon thruster as a general term, it's an electron diamagnetic current that drives the momentum transfer and the generation of thrust. So you can do a bit of theory as well, which is what we did. And as I said at the very beginning, you need to have two fluid systems with electrons and positive ions. You can go through the fluid equations for each particle species, and you can express the electron magnetic drift. You can use your plasma measurements with the probes, and you can recalculate all of these components. So in these curves here, we have the measurements, we have the calculations from this magnetized plasma momentum system. Now, what can we do with the Helicon thruster? So if we dream big, long term, we thought, okay, this is fun. Can we deal with space debris removal if we were to use a Helicon thruster? And we thought, okay, if you want to get into contact with a space debris, you have to accelerate towards the space debris, you have to decelerate, you have to place yourself, and then you have to exchange momentum. It's quite complicated. How could we do that? Well, what if we open both ends of the cavity? So we have an inductive source, but now we open both ends, and we have one solenoid for each end, and we also have one gas injector for each half. So this is what's called the ion beam shepherd proposal that people have published about. So simulations have been done in terms of removing a 1-ton debris, which would be a few meters inside. So with our collaborator in Japan, we did this experiment. There was a dedicated double Helicon thruster that was fabricated and attached to a thrust balance. And to simulate a debris, we had a large disc or plate, which was suspended to pivots so that we could measure any momentum change. And we had essentially two Helicon thrusters attached to each other. And we demonstrated that you could turn one back thruster on and accelerate towards the debris, and this is the momentum that you create that's measured with the thrust balance. We could activate the other half of the thruster. That would be what you would need to do to decelerate and meet up with your debris. And then when you're about to transfer momentum to your debris, you actually have to turn both thrusters on and transfer momentum. So this is the bottom system here. We managed to do that and transfer the equivalent momentum to the debris, which actually moved accordingly to the generated thrust. So this is actually quite quite an engineering challenge, and we're quite happy with this result. So I won't go through this, but people here have put the numbers that are needed in terms of thrust and movement, momentum transfer to the debris, how you would have to decelerate this debris so it could enter and burn into during re-entry. So Helicon thrusters still generate a lowish thrust for 100 watts, although this is being improved year after year. Many people worldwide are working on this, so these are all the laboratories, and there's a very nice review produced by our collaborator in Japan if you want to check more about this. So that's all very good, but that's kind of dreaming, a bit too far. So how about we become a little bit more realistic here? So there's a lot happening with microsatellite constellations and propulsion systems. So you have chemical thrusters, small gridded thrusters, Hall effect thrusters, all being miniaturized. And we thought, okay, how about we just miniaturize this Helicon system? We just get rid of the magnetic field. We just have a tiny, small inductive source, radio frequency powered. So the pressure will be higher, so there will be collisions, and we are going to call it pocket rocket. So pocket rocket, radio frequency micro thruster. We have two versions. We have the capacitive version or the inductive version. I won't go through the details. It's just either a difference in the type of antenna or electrode, which is still around a little cylindrical source. The source is typically 1 or 2 centimeters in length and a few millimeters in diameter. So this is very, very simple. What happens now? It's a smaller cavity. So as we said before, the operating pressure will be higher. There will be a lot more collisions between the ions and the neutrals. And in fact, what happens is the ions, the generated ions, are there to transfer momentum to the neutrals. So it's in fact a thruster that produces heated neutrals, and it's called an electrothermal microthruster. So this would be very cheap. We can run up to a few tenths of watts. And the thrust is not that bad. And it's also quite a safe system. So you can use packages, simulation packages such as COMSOL or CFDAs. Because there are a lot of collisions, it's just much easier to model it as a fluid. So electrons are the fluid. And here we have a system. We are converging, diverging nozzle, where you see these represent the plasma density. And on the right-hand side is another system. But that works quite well. And we have had 4 students work on these pocket rocket students, like PhD, pocket rocket thruster, PhD students. So what do we want to do here? So if we just expel gas, cold gas, into space, we generate thrust. And if this gas exits at the sound speed, with 100 SCCM of argon, you can get about 1 millinewton. So it's not that bad. Now, if we use a little bit of radio frequency to heat the neutrals via ion-neutral collisions, we get to this dmv/dt equation. And if we put 10 watts of radio frequency into heating a gas, we would get a gas velocity of 2.6 kilometers per second, not bad. And considering the 3 degrees of freedom, we can expect a velocity of about 1,000 meters per second. There, which is a thrust gain of a factor of 2 from the plasma. So this is the first experiment measuring thrust with a pocket rocket thruster. It's pretty, bulky and rough going. Anyway, it worked. So we have here a cylindrical radio frequency source. It's attached to an impedance matching system, and this is within a vacuum chamber and attached to a thrust balance. This was done in collaboration with Lockheed Martin in the US, by the way. But anyway, we showed that, you have a cold gas thrust component. And as soon as you put radio frequency power and you ionize the gas to become a plasma, you can see that you get an additional thrust component related to heating of the gas. What happens is when you heat the gas, you have volumetric heating due to the collisions, but you always have ion bombardment onto the walls of the cavity. And the ion bombardment can also generate wall heating. So it's an electrothermal thruster with 2 heating systems. There's the first one, which is volumetric, and there's a wall one. We had a little bit of a surprise. We thought, oh, that's great. How about we use nitrogen in pocket rockets? And we quickly found out that if you use a molecule, you have a lot of electrical power that's just trapped into the vibrational states of the molecules. And that is never converted to kinetic energy or thrust. So you should not really use, nitrogen is not a good propellant. It would be better to continue with argon, krypton, or xenon. That being said, being able to increase the vibrational temperature using pocket rocket has very important application for exoplanet research. And I won't have time to go through this. So although it's not very good for an engineering application, it has a research application which is being carried out at the University of Rennes in France at the moment. So this here is the measurement with a much better thrust balance, with a better sensitivity, is what happens with the thrust generation of pocket rocket as a function of time when you turn the plasma on. The moment you turn the plasma on, you have this increase of thrust, which is measured with the displacement of the balance. And as the time proceeds, you have this resistor jet thrust component, which corresponds to the walls of the plasma cavity heating up and then heating your neutrals as well. So this is a confirmation that any small inductive source would work as a thruster, very small, very simple thruster. Now, we're still not in space. How do we get to launch? I'll just check the time here. Okay, going well. So it's always really hard to measure thruster performance. And we decided to work for a while on setting up our own testing infrastructure. So we developed our thrust balance. We have a few vacuum chambers, but ideally you really want a much larger thermal vacuum chamber. So this is, in fact, a photo of Wombat XL at the INU Stromlo campus. I don't know if you've heard about the AITC, the Advanced Instrumentation Technology Center. So this is a 3-meter diameter, 6-meter long vacuum chamber. And on the left-hand side here, you can see that it has a second module, which is called the propulsion module, which you can see here in much better detail. So the propulsion module has a thrust balance, is designed for thruster qualifications. And the right-hand side here, you can put, has got the thermal shrouds and has cryogenic panels, a really large pumping speed, and you can put a whole satellite in it up to 1 meter square. So we have an example of a Helicon double layer thruster attached to the thrust balance and immersed and firing into Wombat XL. At the ITC, they also have a shaker. We also very soon will have our own shaker in our lab on the main campus at the ANU. That's in the Research School of Physics. And they have CubeSat pods if you want to do testing, clean a room, and anechoic chamber. So for us, we decided that we wanted to move a little bit in the CubeSat game because that was the only way to get into space. So we also developed our ground station in our SP3 laboratory. And so we have a system of UHF and VHF antennas, and this is the control system for our ground station. So the antennas are just on the roof above our lab. So we have infrastructure in terms of thermal chambers, thermal vac chambers, but we needed some practice. How do you get into space? So we practiced with the QB50 European project. So this didn't have propulsion systems, but it was organized by the EU, and it was a collaboration between about 50 universities where each university would actually have its own CubeSat with different payloads. And the goal was to just learn how to go through the whole process. And the scientific goal was to study the lower thermosphere and the ionosphere of the Earth. So it had some special plasma and gas sensors that were designed by SSTL in the UK. And in particular, it had what's called INMS, a little mass spectrometer or energy analyzer, which is this unit here. So Australia was involved with the development of 3 QB50 CubeSats, and we are involved in one of them in particular, ANU Sydney UNSW. So the 3 of those CubeSats were actually tested in Wombat XL. And it was a very steep learning curve on the different process required for getting into space. But we did get into space, and we published the results. So these are the three thrusters being deployed from the International Space Station. It was really fascinating. And this is what we were doing with our space station. We could see all of these CubeSats orbiting around the Earth. It was kind of really fun. So in the process, we managed to put a little bit of double layer physics in there. And so that was with our collaborator, Dhiren Kataria from SSTL. He's the one who designed one of the sensors that was on 8 of those QB50 satellites. And he brought the space version here into our laboratory. And we decided to use a double layer to create a plasma wind tunnel experiment. So here you have the radio frequency thruster with the double layer somewhere, and we have our energy analyzer to make sure that we have an ion beam which is created properly, and then we created a differential pumping, so by cutting the diffusion chamber in half and having a plate which is an aperture hole, and then we put his space space CubeSat on the right hand side. And why was this needed? Well, in fact, at SSTL, they could not really do any proper ground-based calibration of their sensor for energies lower than 100 electron volts. So what's a wind tunnel? Well, it's quite straightforward. In orbit, the satellite will be at a velocity of 8 kilometers per second and orbiting in the ionosphere. But here in the laboratory, what we do is we have a stationary satellite, and we are shooting ions with the velocities of 8 kilometers per second. So it's the opposite, but effectively it's the same outcome. So anyway, so we played with different baffles, different extractions. We measured the ions. And we managed to do some calibration, and we managed to demonstrate that you can use a double layer to generate a plasma double layer wind tunnel. So that was kind of fun. Well, we are still not in space as such. So we decided that if you really want to go into space with the radio frequency system, you have to miniaturize the impedance matching system. So instead of having usually what's called a big matching box with variable capacitors to be able to tune the plasma to the 13.56 megahertz frequency, which is a standard commercial frequency, we can use what's called a frequency variable impedance matching, where you have a system of ceramic capacitors and you change the frequency to tune and get the optimum power absorption into the plasma. So this was demonstrated here for an early version of the Helicon thruster. And then we worked with the Stanford Electronics Laboratory, Stanford University Power Electronics Department, to try and develop a miniaturized radio frequency subsystem for the pocket rocket thruster. So you can see the first version here with batteries, and well, it's us being much younger. So yeah, oh, that's a long time ago already. So the idea is that when you make radio frequency amplifiers, you have different types of amplifiers, but the most efficient one is typically a class C to E. So we use a version of a class E, and we had a very good efficiency. And after that, we worked with other PhD students at Stanford, and we just made even more progress with this. So this is another amplifier powering the inductive pocket rocket. And here is a more elaborate with a bus and an onboard computer access and a battery system still powering a pocket rocket. And then we combined all of this into simplifying as much as we could, making it simpler, more cost-effective, just a few parts, and fitting it within a CubeSat form, which is 10 centimeters square. And we're demonstrating it ignition and tuning with no parasitic discharge, and that's actually the basis of a patent with Stanford, between Stanford and INU. We also developed a little gas propellant subsystem, which is essentially a canister that you can use to pump up your bike tire, except that it contains argon. Checking the time again. Yeah, okay, great. And so we demonstrated the pocket rocket concept and reached what's called technology readiness level 7. So we were very happy with that, but still not in space. So one of our students decided to further simplify the system and thought about, okay, what's the absolute simplest initially cold gas thruster that we can use. And he thought about using naphthalene as propellant. So C10H8, it's quite heavy, and the advantage is that it sublimates at room temperature. So what you need to heat it up, release it, and you should get thrust. And it's not corrosive. So he made a proof of concept here, and you can see the displacement of the thrust balance when you open or close the valve. He also optimized the thrust balance sensitivity, because this is now pretty small thrust values. So this is a prototype that's suspended to the thrust balance. And this is now within one of our space simulation chamber in the laboratory. And what happened is Boswell Technologies sponsored the launch and the development of what we call the Bogon cold gas thruster, which was embedded within a three-unit CubeSat 4. And there was a joint development and 2 launches that were organized via a Skycraft satellite mission. And this happened about 2 or 3 years ago. And finally, there was technology readiness 9 and in-orbit validation of the Bogon thruster that was demonstrated and achieved via this local development. So thank you to Boswell Technology and Skycraft for doing this, and of course to the SP3 lab, as we did all the development in SP3. Okay, to finish, I will come back to Earth and talk a bit more about other applications of inductive and wave radio frequency sources that we've worked on over the years. So you have presented Wombat Extra Large, which is at Mount Stromlo, but for the past few decades, we've had just a Wombat vacuum chamber in the laboratory. It's 1 meter in diameter and 2 meters in length. And up to now, it had a limited pumping capacity. But right now, we are upgrading it, and we have installed 3 major turbo pumps and a mass spectrometer and RGA. And this is it's not commissioned, but this is what's happening right now. So this will be in parallel with the shaker developments and with another thermal vacuum chamber within this chamber. So soon we will be fully equipped with a very flexible and very active space capability measurement system. So in terms of flown technologies, you may have heard about the kinetic T6 thruster that's currently on its way to Mercury on a Bepi-Colombo spacecraft. So why is this important? I think there was a DW seminar, the previous one, on focused ion beams. And so it kind of relates to ion gridded thrusters as well, because you have a plasma cavity, a system of grids, and all these beamlets coming out. So there are many applications of ion sources. So Bepi-Colombo has got 4 of these thrusters, and it's on its way to Mercury. We did some work with them, and that's with the European Space Agency. So it's in its deep space activation at the moment, or travel phase at the moment. But we've been also working on how you apply radio frequency sources to the development of focused ion beams. So we've been doing this for nearly a quarter of a century. Really, that's scary. And that was also related to the dual stage 4-grid development of the thruster, and also to the Oregon Physics Hyperion ion source that is a commercial project now via Oregon Physics in the US. So this is the first source that we had at ANU. Just always a cylindrical tube and a high voltage electrode, this time immersed here at the top, and a system of electrodes to be able to extract the ions. And when you work on this, you realize that there are serious problems like inter-electrode breakdown, secondary discharge, differential pumping, RF interference. But anyway, so on the right-hand side here, you can see a photo of another propulsion device that we developed, the DS4G, which was a radio frequency ion gridded thruster that was in collaboration with the European Space Agency. It worked really well. It had a really high specific impulse, nearly 20,000 seconds. That's huge. That's the highest ever measured. However, the power system to run it is just not available for space. So once there's progress with power subsystem miniaturization, then there might be some hope. But at the moment, that's a limitation. So we kind of stopped working with that and we focused more on ion extraction for FIBS. So I think you've heard about this before, so I won't go through the details. Here you can see what the Hyperion source looks like. And you can do very fast milling. It works with xenon or different gases. But what we are focusing on here in the laboratory is the generation of an O3 minus beam, so negative ion beam. So that means that you need to have a transverse magnetic field to get rid of the electrons and extract the negative ions. So there are different ways of doing this. Won't go through the details, but why do we want to do this? This actually is very important. There is a professor in pathology at the Stanford Medical School that has developed a way of doing imaging of cells using negative ion beams. And he can separate cancerous cells from non-cancerous cells. So this would be a very nice application if we can master this diagnostic and somehow master the process. And the final application, which we did along the way, which kind of went up and down, we worked a lot on hydrogen fuel cell development. And in the process, we again use a radio frequency Helicon source to do deposition and growth of carbon nanofibers and to do cluster deposition of catalysts on these carbon nanofibers to increase the efficiency of the fuel cells. And that worked really well. And the goal was to reduce the amount of catalyst that you need when you actually make a fuel cell electrode. And the amount of catalyst was reduced by a factor of 100. So fuel cells are not so popular these days. It's more electric cars rather than fuel cell cars, but who knows what's going to happen. So right now, I would like to thank you very much for your attention. And I hope that I've given you an example of what can be done with Helicon double layers in general and thrust applications, and more broadly speaking, applications of a radio frequency plasma source. Thank you very much for your attention, and it's open to questions.
Thank you, Christina, for the wonderful presentation and all the rocket science you were able to put in.